So now we're going to talk about a specific kind of power function called a polynomial function. And these are the kinds of power functions that you're probably the most familiar with because you've studied polynomials ever since you started learning about algebra when you were much younger, probably. So polynomial functions are power functions in which the powers are non-negative integers. For example, f of x is equal to 4x squared plus 3x minus 7. So if you look at the powers here, we have a power of 2, a power of 1. This would be a power of x to the 0 power. So all of those are non-negative integers. Here's an example of something which is not a power function. G of x is equal to the square root of x plus 1 over x. This is not a power function. Not a polynomial. It's a power function, but not a polynomial. And why? Because this is x to the 1/2 power, and this is x to the negative 1 power. And when we look at these powers are not integers that are not negative. So g of x would not be a polynomial. So just to review some polynomial vocabulary, which I think you're already familiar with, the lead coefficient is the number the coefficient of the leading term. Once the term has been, the polynomial has been put in what we call standard form, meaning that it has been arranged from highest power to lowest power. And that's usually how you see them written anyway. The leading term is the first term here once it's been in standard form. The degree is the degree of this term. So we would say the leading coefficient here was 6, the lead term was 6x to the 5th, and the degree was 5, because that's the degree of the leading term. Let's take a look at another example. So f of x is equal to 3 plus 5x squared minus 6x to the 6th. Before we can start talking about these things, we have to first put it in standard form. So we're going to rearrange it from highest power of x to lowest power of x. And now we can talk about the lead coefficient. The lead coefficient would be negative 6. The leading term would be negative 6x to the 6th. And the degree of that term would be 6. The end behavior of polynomial functions are determined by its leading term. Another way of saying that, you'll often hear it said, the behavior is dominated by its leading term. So for example, if we come back here and we look at these two polynomials on our previous slide, we can talk about the end behavior of each one. So since they're power functions, we already know how to analyze their end behavior. When we looked at this first one, we'd say, oh, the power is odd and the leading coefficient is positive. Since the power is odd, we know that the arms point in opposite directions. And since the coefficient is positive, we know it's a rising function. So something like this. So this left arm is down and the right arm is up. If we were to write that in arrow notation, we would say, as x approaches negative infinity, on the left side, the function is getting smaller and smaller, going to negative infinity. And as x approaches positive infinity, meaning it's larger and larger, we can see that f of x is also getting larger and larger. F of x is approaching infinity. Let's go ahead and review that for the second function. For this second function, we would look and go, oh, this is an even function, and the leading coefficient is negative. So we know that since it's an even function, the arms point in the same direction, and since the coefficient is negative, they both point down. So something like this. So if we wanted to describe the end behavior in arrow notation, as x approaches negative infinity, the function values are getting smaller and smaller. They're going down. And as x approaches positive infinity, the function values are also getting smaller and smaller. The function values are approaching negative infinity. Now, when you want to talk about the end behavior of a polynomial, you have to have it in standard form. This next example, the polynomial comes to us in factored form, which is convenient for some things, but not for determining end behavior. So if we wanted to determine the end behavior of this polynomial, the first thing we would need to do is we would need to start multiplying it together. So f of x is equal to negative 2x cubed times, we'll multiply those two binomials together. That would give us x squared minus 3x minus 10. And then we could begin to distribute, but I'm only going to distribute these first two terms because I know that this is going to give me the highest power of x. All the rest are going to be lower. So in order to discuss the end behavior, I just need to know what the dominant term is. I just need to know what the first or the leading term is. Odd with a negative coefficient. Odd means the arms point in opposite directions. Negative coefficient means it's falling as we go from left to right. And so we can write its end behavior in arrow notation. So as x approaches negative infinity, the function is going up, it's getting higher and higher, it's approaching infinity. And as x approaches positive infinity, we can see that the function values are going down, in other words, getting lower and lower towards negative infinity. With polynomials, not only do we care about the end behavior, we also care about the local behavior. So two features of a polynomial that we're very interested in are intercepts and turning points. So the intercepts are the places where the polynomial crosses the x-axis. And there's also a y-intercept as well, but often we're just concerned about the x-intercepts because those are the roots of the polynomial. And the turning points are the places where the polynomial literally turns around, goes from going up to going down, or goes from going down to going up. So this polynomial in the graph has 3 x-intercepts and 2 turning points. To find the x and the y-intercepts of a polynomial, the first one that's easy to find is the y-intercept, and we've talked about this before. So to find the y-intercept, you're going to just evaluate what f of 0 is equal to. So in this case, f of 0 would be equal to, if you plug in a 0 for x, we would have 2 times negative 4 times 5, and that would be equal to negative 40. So the y-intercept would be the point 0, negative 40. In other words, it's going to intercept the y-axis at negative 40. For the x-intercepts, we're looking for the roots of the polynomial. In other words, where is the polynomial equal to 0? The roots of a polynomial are very easy to find if the polynomial is in factored form, which this first one is. Because remember, a product can only be equal to 0 if one of the factors is equal to 0. To find the roots of this polynomial, we would simply have to take every factor, so the first one, x plus 2, and find out when it's equal to 0. So one root would be negative 2. We would take the next factor and find out when it was equal to 0. So another root would be 4. And this one has 3 factors, so we would take the third factor and find out when it was equal to 0. And by solving that equation, you could find out that the third root happened at x is equal to negative 5/3. So y-intercept, really easy, just find f of 0. For x-intercepts, you need to find the roots of the polynomial, which is easy if the polynomial is in factored form. However, not all polynomials come to us in factored form. So what if we wanted to find the intercepts of f of x is equal to 3x cubed minus 3x squared minus 18x? Well, the y-intercept is always very easy to find. If I wanted to find the y-intercept of that function, I would simply have to find f of 0. and f of 0 would be equal to 0. So this function crosses the y-axis at the point 0. In other words, it goes through the origin. But the x-intercepts, that's a whole nother story. For the x-intercepts, we would have to be able to factor that polynomial, and if it wasn't factorable, we would have to use technology. So most of you have done this before, how to find the roots of a polynomial on your calculator. I'll post some links to videos, but you could also YouTube this yourself and just find some videos that remind you of the process, and I'll also demonstrate it during class. So let's go ahead and why don't you see if you can do this one? I'll get you started. So to find the intercepts of f of x is equal to 2x plus 1 times x plus 3 times x minus 1. To find the y-intercept, you need to find out what f of 0 is, so plug in 0 for x. And to find the x-intercepts, you have to take each of these factors. Now notice there are 1, 2, 3 factors. Set them equal to 0 and solve, and so there's going to be 3 values for the x-intercepts. And then for the next one, you'll have to use technology and round your answers off, let's just say to 1 decimal place. Okay, so you might need to pause and YouTube how to do that if you don't remember, but why don't you give both of those a try. Now, sometimes when you're looking for roots of a polynomial, it's nice to know how many to expect. So a polynomial of degree n can have at most n x-intercepts and n minus 1 turning points. So here's an example. Find the maximum number of x-intercepts and turning points for this polynomial. If we look at this polynomial is degree 5, so it can have at most 5 roots and n minus 1 4 turning points. Here's one last one for you to try. Find the maximum number of x-intercepts and turning points for this polynomial. So the first thing you're going to do is look at its degree, and then from there, figure out how many roots and how many turning points.